Okay, welcome everyone. It's a great pleasure to host with us an old friend, Dr. Vassily Mewes, currently at Oak Ridge National Lab in the United States. Vassily did his studies in Cambridge and completed his PhD in the University of Valencia. He was a postdoc concurrently with me in the Rochester Institute of Technology in the United States. And as I said, is now a researcher at the Computational Science Center at Oak Ridge National Lab. He will talk to us about SphericalNR, a new framework for post-merger simulations of binary neutron stars. Vassily, take it away.
All right, Ovik, thanks a lot for the invitation. And yes, so I'll talk about a code that I'm the lead developer. And Ovik told me there's going to be students in the audience, so I'll try to give some sort of overview, what we need to do, what the state of the art is, and then some algorithmic challenges that we faced in developing the code, and then some outlook, what is still needed in the future. But it is about doing numerical relativity in spherical coordinates. So we've all seen that plot. We've entered the era of gravitational wave multi-messenger astronomy. So we've detected binary black holes, and they're being detected at an ever-increasing rate. We have electromagnetically bright neutron stars, and then obviously we had the detection of a binary neutron star merger. We also have electromagnetically bright black holes, where they're basically in binary systems and accreting from a secondary. I'm not going to go into the details here. I'm just indicating here there's a mass gap here between what would be the highest mass neutron stars that could collapse to black holes, and then the lowest black hole masses we actually observe in those binary systems. And the existence or not thereof seems to depend on the precise supernova explosion mechanisms. And I was fighting with the referee in one of my big first papers as a PhD, where the referee basically told us that our simulations were completely unrealistic because of the existence of that mass gap. So it would be nice if somebody in the future could reactively prove us right and say that the simulations we did were actually physically motivated. But basically, we need to do simulations of these systems in order to predict their outcomes and then contrast those predictions with reality and observations. And here's an overview of the systems we're actually dealing with. So we have mass on the left going down, and then we have different systems. So we have binary black holes that are thought to be electromagnetically dark. We have binary neutron star mergers that are gravitationally wave and electromagnetically bright, and then black hole neutron star mergers. And further down, we have supermassive binary black holes, which happen in galaxy mergers. So those are obviously gravitationally wave bright and electromagnetically bright. And with the different, because the masses change what the frequency of the systems is, you need different detectors. So the supermassive binary black hole mergers are going to be detected or are being seen electromagnetically first, and then later when LISA and the PTA comes along, we're going to see those in gravitational waves as well. And I'm not going to go into supernovae, but obviously supernovae are electromagnetically neutrino and gravitation wave bright. And I guess the key take-home message is that multi-messenger astronomy requires multi-physics simulations. So you have the 3 different carriers: gravitation waves, electromagnetic radiation, and neutrinos. And those have different physics and different numerical techniques that you need to actually employ when you self-consistently perform simulations of these systems. So you have general relativity, which then becomes numerical relativity. The gravitation waves, can I move that? Yes, okay. The nuclear physics and thermodynamics via the equations of state change the gravitational waves. You have self-gravitating matter. Then you have electromagnetic radiation from jets, where you need GMHD and radiation physics. And finally, you have neutrinos, where again you have nuclear physics and you have neutrino transport. So you can either do neutrino leakage or truncated moment radiation hydrodynamics, and those change. Those are important, for instance, in the post-merger phase, when you form a hypermassive neutron star. So the star can cool by emitting neutrinos and then collapse earlier or later. So you need to self-consistently solve all those different physics together, which is hard. And I'm going to go into detail what we've done to do that in a coordinate system that is adapted to the symmetries. Right. So what are we actually doing? We are numerically solving the Einstein equations. So on the right-hand side, you have the space-time part, which is the Ricci tensor and the metric tensor together with the Ricci scalar. And basically what the Einstein equations are telling you is how space-time is curved, and the stress energy content of the space-time, which is both the stress energy content of the metric or the gravitational field and the content that comes from all the matter contributions, form that from this set of highly nonlinear partial differential equations. So you have mixed elliptic hyperbolic partial differential equations for the space-time part, and then for the matter part, you usually have hyperbolic conservation laws. And that can include, as I said, neutrinos go in there, and normal fluid dynamics and magnetohydrodynamics. It's covariant, so there's 4D, so in space and time are on equal footing. And that makes it difficult to solve this numerically, right? So the beauty of general relativity and the 4 times covariance of space-time makes it difficult, because in our experience, obviously, we don't perceive space and time of being of the equal footing. We have 3-dimensional space and we move forward in time. And then you also have, from like thermodynamics, you have a preferred error of time. So ideally, we want to solve those equations in a way that is more akin to how we see the world. And that is basically being done with the 3+1 formalism and the ADM formalism. So we slice the 4-dimensional space-time as a family of non-intersecting space-like hypersurfaces. And then you have 2 quantities, which is the lapse and the shift, which indicate how the time and the coordinate changes between those surfaces. So what you then do is you start with initial data after you've done your split, and you have the 3 metric on each hypersurface, which is a subpart of the 4-dimensional space-time metric. And you can then formulate the equations which are 4-dimensional in terms of a Cauchy initial data problem. So you prescribe your initial data on the space-like hypersurfaces, and then you use the actual evolution equations to integrate those forward in time. And then the lapse and the shift basically show you how the time coordinate changes between the different hypersurfaces, and the shift shows you how the coordinate changes. So in each hypersurface, you can choose spatial coordinates as you see fit, and the freedom of choice of the spatial coordinates in the hypersurface together with the lapse and the shift are an equivalent way to expressing the 4-dimensional covariance of the equations. So those are 2 fully equivalent ways of seeing the evolution equations. And when you do that, you basically end up with the 3+1 ADM evolution and constraint equations. So you have a evolution equation for the metric, where you have the lead derivative, so the time derivative minus the lead derivative of the 3 metric is given by the extrinsic curvature. So the velocity of the metric is equal to the extrinsic curvature, which is a measure of how the curvature on the hypersurface is embedded in the 4-dimensional manifold. And you have an evolution equation for the extrinsic curvature as well. And finally, you have 2 constraint equations. So I said earlier that the space-time part of the Einstein equations is mixed hyperbolic elliptic. So the first 2 are 2 hyperbolic evolution equations, and then you have elliptic constraint equations. And those constraints analytically are fulfilled at all times. So if you start with constraint preserving or with constraint fulfilling initial data, then the evolution equations are basically in such a way that going forward, those will always be fulfilled, but numerically, that's obviously not true, and that's one of the problems with solving these equations numerically. I'm not going to go into the constraints because that's a whole other field of how to actually solve for initial data. So in this talk, we're going to assume that we're going to get constraint fulfilling initial data, and then we're just going to evolve them forward in time. And then finally, you have various projections of the stress energy tensor that give you the matter sources. So you have the matter energy density, the matter momentum density, and the matter stress energy tensor, and finally the trace. So all those go in there. And if you, let's say you want to solve for a neutron star, an equilibrium model of a neutron star, then you have to solve the equations of hydrostatic equilibrium together with the momentum and constraint equations, and then basically end up with initial data that you can then evolve forward in time. There's one problem with that, however. So that was being done in the early stages of numerical relativity. And people soon found out that the equations as posed here, the evolution equations, are not actually strongly hyperbolic. And the problem is, if you see in the extrinsic curvature evolution equation, the Ricci tensor, the 3 Ricci tensor appears there, and you basically have mixed partial derivatives, second partial derivatives of the metric, which spoils the hyperbolic character of the equation. And if you actually code those up and evolve initial data that is constraint fulfilling, then your evolution will quickly blow up due to the fact that the equations are not well posed. And this is where one of the most famous formulations for numerical relativity comes in, which is the BSSN formulation, which is after Baumgartner, Shapiro, and Shibata and Nakamura, where you basically rewrite the ADM evolution equations by introducing the conformal traceless reformulation. And you basically use a conformal decomposition of the spatial metric. So you define your the conformally related metric in this way, where you have the conformal factor given by the ratio of the determinants of the full spacetime of the full free metric and the conformal metric. And you also introduce a conformally related traceless part of the extrinsic curvature. And finally, you introduce conformal connection functions, which are now independent evolution variables. And those now contain those mixed partial derivatives in the original Ricci tensor. And because you evolve them separately, the new evolution equations that you get with this system are strongly hyperbolic. And that is arguably one of the most useful and most used systems. So 2 of the 3 breakthrough simulations of binary black holes in 2005 and 2006 used the BSSN formulation. And then finally, we have the matter. So I'm gonna, in this talk, I'm gonna only concentrate on magnetohydrodynamics. So the matter evolution is governed by conservation laws for the stress energy tensor and matter currents. So we have the continuity equation, and then we basically have the conservation of stress energy. And then you basically sum the contributions of the matter, of the baryonic matter and the electromagnetic fields. And then finally, we have to also solve Maxwell equations. And the assumptions that we're going to do here is that we have a perfect fluid, and we're going to be in the ideal MHD limit. So the stress energy tensor is going to be given in the following form, where H is the specific enthalpy, and the start pressure is the combined pressure of fluid and magnetic field. Then a big slide here. I started that slide when I first gave a talk like that a couple of years ago. So if somebody's in the audience that has a code that is not on here, I apologize, and please send me an email or drop me a note that I can include it. But basically, and I'm focusing on the Einstein toolkit because that's what I've been working on since I started my PhD studies almost a decade ago, I think. So the Einstein toolkit is an open source code suite for relativistic astrophysics, and it provides you with a mesh, and you have box-in-box moving adaptive mesh refinement. And you, as a physics computational physicist, you can use the toolkit, and then you can basically supply your own evolution equations. And then it's quite nice in the sense that you just have to write down the right-hand sides and calculate the right-hand sides, and then everything else is being taken care of by the toolkit. So you don't have to worry about time integration and these things. There's a method of lines already implemented. And nowadays, in numerical relativity, we basically, as I said, there's different codes and different groups that use different formulations. So you have BSSN or ZZZ4. So those are free evolutions, as I said before. ZZZ4 is constraint damping. There's a plethora of codes that use those. There's pseudospectral codes. There are people starting to work with the spectral code using DG methods. And there's a generalized harmonic formulation. So that is being done for the spacetime part. So those can be vacuum simulations or coupled to matter. And for GMHD, the state of the art is basically using high resolution shock capturing methods for hyperbolic conservation laws. And then you need to fulfill the solenoidal constraint of the magnetic field. So we know there are no magnetic monopoles. And if you evolve the induction equation in a straightforward way as a normal hyperbolic PDE, you'll notice that, sorry, dry air. You'll notice that the solenoidal constraint is only fulfilled up to truncation error. So as you integrate the equations forward in time, diff B violations will actually grow, and those spoil the simulation. So they introduce fictitious forces, and they're really bad. So one of the main things in GMHD is actually fulfill the diff B constraint. And there's different techniques. There's constraint transport, constraint damping, or you can evolve a vector potential and then take the curl. And again, there's a plethora of codes that actually have solved this problem and can do self-consistent simulations. And finally, you have to have an equation of state that is more realistic than just polytropes and ideal gases, so to include microphysics. And nowadays, the state of the art is using temperature and constitution dependent equations of state, just like that's being done in the supernova field. And here's a list of equations of state that have been used in binary neutron star mergers. And the final one is neutrinos. So that is something where the supernova community has been much ahead of the game in terms of the binary neutron star merger community. So they've been using truncated moment formalisms or more approximate neutrino cooling and heating in their simulations for decades now. Whereas in our field in numerical relativity, we're only catching on there. So there's different, so the most simple thing you can do is a leakage scheme where you radiate away energy by neutrinos, and then you assume that the neutrinos don't interact with the matter anymore, and they just remove energy and momentum from the system. But you can also have the neutrinos back reacting on the matter, and that is being done more and more consistently in more modern codes. Okay, I talked about the state of the art, and what I did during my PhD is simulations of tilted self-gravitating accretion tori. So if you think about a black hole neutron star merger, if the black hole spin is misaligned with the orbital angular momentum, the neutron star is going to be tidally disrupted, and you're going to form an accretion disk that has its angular momentum aligned with the orbital angular momentum, right? Because that's where the bulk of the material is going. But the spin was misaligned of the black hole, and the spin of the black hole is not necessarily going to be changed during the orbit, which means that you end up with a system where the black hole spin is misaligned, and that creates completely new dynamics, because now the ISCO is an ellipsoid, so material will start entering the ISCO at different angles, and you get bending waves inside the disk, and it depends on how fast the sound crossing time is in the disk, whether those bending waves are diffusive or going through the disk faster. So I did a large parameter study during my PhD on those systems, and we were studying hydrodynamic instabilities in those accretion disks in the presence of tilted black holes. And here is a video of one of those simulations. So you see that the disk bends around, it feels the tilted spacetime, and you see those two streams coming in and attacking the ischia from different directions. And you see there's an instability and a wobbling, and then the disk moves around because the north-south symmetry of the system is broken, and you start getting linear momentum. And here's a top view of the system. We used some tracer particles that is going to show the development of the Papaloisa-Pringle instability, which is a hydrodynamic instability in the torus. So you start going around, and then you're going to see that you form an azimuthal m=1 over density feature in the disk. That basically forms a binary system with the central black hole. So both the black hole and the lump that is traveling around in the disk form a binary system and wiggle around. And those emit gravitational waves. And we quantified that. And then again, the referee that was mean to me as a PhD student basically told me that it wasn't realistic because of the mass gap. So I'm hoping that somebody comes forward and answers the question of the mass gap definitively. Those were done with the Einstein toolkit, the original one.
I think there's a question.
Oh, sorry, I cannot see anything.
Yes, I have a question.
Yes.
But I think that the second plot answered my question, the time scale of the process. But I see here it's milliseconds.
Yes, yes.
Okay. Because in the first simulation, I didn't see any time scale, right? I saw only the number.
Yes. So the first one was in code units. So C equals G, big G equals the solar mass equals 1.
Okay.
So one time unit is 4.9 microseconds. And in the second one, I introduced milliseconds.
Okay, fine, thanks.
I have a question.
Yes.
You're going to, since you use the Einstein toolkit, what's the ratio of masses of the disk to the central black hole that you assumed here?
So the one on the left was 0.1 and the one on the right 0.8.
0.8. Oh, that's
0.08. Sorry, 0.08.
Okay, so basically that means that the metric is very barely affected. You can simply use the Kerr metric, and that's it, right?
Well, I mean, you saw that it is affected because you saw the black hole wiggling around, right? So, and we also see that the spin is processing. So I can talk about that in more detail later, because those simulations are only the motivation of what I'm actually going to talk about. But at those mass ratios, and again, it's debatable if those actually exist after those mergers, because you need very low black hole masses and high neutron star masses in order to actually form a disk that is heavy enough. But at those masses, the spacetime is certainly feeling the effect of the matter. So that's enough. It's not enough anymore to be perturbative. So you see that the black hole moves around and the spin is processing, because you form solid. The disk is basically processing as a solid body because the disk is compact and the sound crossing speed is low. And that precession is equal and opposite in the black hole spin. So.
Okay. Which I assume that goes, maybe going back to the referees, the question that you mentioned, which was definitely not me, just to clarify. Is there any system in astrophysics that would you expect to see such high ratio of masses of disk to black hole?
Yes, I mean, that depends on if that mass gap exists or not. If it doesn't, then you wouldn't expect to see these mass ratios, right? Because the larger the black hole, the harder it is to actually tidally disrupt the star and actually form a massive disk, right? So you need a low mass black hole with high spin and a neutron star. So you have to have the perfect combination. If it's in untilted systems, in core collapse supernova, you can get really heavy disks around the central black hole, right? Because you have so much more material from the collapsing star. But in those systems, normally you wouldn't expect the black hole spin to be misaligned with the orbital angular momentum of the fluid if it's rotational core collapse, because I mean, there's no way to, I mean, the star is rotating uniformly or differentially rotating, and then it collapses, so the black hole spin will be aligned. But the gravitation waves from the Papalousi-Pringle instability, where you basically form the binary system between the overdensity and the black hole, that is more favorable in core collapse supernova because you can get large disk masses there. Anyone, or can I go on? Okay. All right, so those were done with the Einstein toolkit with the Cartesian version of it, because spherical coordinates didn't exist in the Einstein toolkit back then. And here's some shortcomings. So in Cartesian box-in-box mesh refinement causes the loss of energy and linear momentum at mesh refinement boundaries in the material. You can cure that with a technique called refluxing, where you basically match the fluxes across the mesh refinement boundaries. But that is expensive, and I didn't do that in my simulations. And even if you do that, so the space-time is always going to be noisy. So if you think about, we had the black hole here, that is the actual grid evolution of the simulation I showed before. You have the black hole in the center and it starts moving around, so you will emit gravitational waves, which are approximately spherical waves traveling out. So you're going to have reflections at the faces and at the corners, which is why in Cartesian simulations you always see fictitious m=4, l=4 mode in gravitational waves, and that's basically due to the partial reflections at those mesh refinement boundaries. And you cannot at those simulations in Cartesian coordinates, because the number of the total points goes to the cube. You cannot just use the same high resolution at the center that you need for the black hole in the entire domain, because the outer boundary needs to be causally disconnected from the system, because that's the one part where in BSSN there's no well-posed outer boundary. So what people are basically doing is you put the outer boundary very far away, and then you say, if it's causally disconnected from the dynamics of the central system, it will not, the errors propagating in from the outer boundary will not affect the evolution of the system. But that is prohibitively expensive, and nobody would give you computational time to actually set up a Cartesian block of like 10,000 cube points in order to do those systems. And maybe most importantly for accretion disk physics, and that is something where the GMHD accretion disk physics community in fixed background spacetimes around Kerr black holes has always criticized work in numerical relativity as well, is that Cartesian meshes do not conserve angular momentum. And that is because the flow is not perpendicular to the grid face, so you get truncation errors in the angular momentum, and that might enhance the accretion or decrease the accretion depending on how you look at it. So is there a coordinate system that has these features, or the features that we want? And the question is, there is, which is spherical coordinates. And so we started when I moved to RIT. Before Ulfric came there. I was there a bit early. I started developing SphericalNR, which is a new framework for numerical relativity in spherical coordinates with the Einstein toolkit. So there's different problems with spherical coordinates. So first of all, you need a mathematical foundation, because solving hyperbolic PDEs using finite differences and finite volumes in spherical coordinates is difficult, because you have the origin and the axis, so you have true coordinate singularities there. And we needed algorithmic development. So the Einstein toolkit was inherently Cartesian. The coordinates are called x, y, z, and we needed to actually trick the Einstein toolkit into thinking that it's still doing its stuff in Cartesian coordinates, and we actually use spherical coordinates under the hood. And we wanted to enable spherical coordinates while being able to use as much of the existing infrastructure as possible. And then finally, there's a big problem with spherical coordinates in that the cell volumes are not constant in spherical coordinates. So as you go towards the origin and towards the axis, the distance between cell centers becomes increasingly smaller. And if you solve hyperbolic PDEs, then you're going to be time step limited by the CFL condition. So you need to do something about the severe time step restrictions in spherical coordinates. And finally, writing down the BSSN equations in Cartesian coordinates by hand in the code is already a tedious task and error prone, but writing it down for spherical coordinates is even worse. So we opted for automatic code generation to generate the right-hand side codes by using Python. And then I'm going to go through in a bit more detail for all of these. So here's an overview. We solved the covariant form of the BSSN equations, which have been derived by Brown in 2009, and Alcubierre in 2011 has a nice paper where it goes into more detail. So those would be the two background papers. And we're basically using a spherical coordinate reference metric where we express the conformally related metric as a sum of a fixed background metric plus corrections. And those are not small, so it's not a perturbative approach. And we did that for vacuum first. We then added ZZZ4, the constraint damping, and GMHD, and that has been published. And we're currently working on the filter to ameliorate those severe CFL restrictions. And we're filtering both in the theta and the phi coordinate in order to almost get rid of the time step restrictions of both angular coordinates. And by now we have support for arbitrary radial coordinates. So we can use generic fisheye coordinates or something like exponent of R, which is used in accretion disk simulations. And that is currently still in preparation. So here's what we do when we evolve hyperbolic PDEs in spherical coordinates. So as I said, you take the conformally related metric and you split it up as the background plus HIJ. The HIJs will be our evolved fields. And you introduce an orthonormal basis with respect to the background metric. And in our notation, plain Latin indices denote coordinate basis components, and the curly braces denote orthonormal basis components. And every time you encounter partial derivatives that you want to solve via finite differences in the code, so a term like the partial derivative with respect to the K component of Hij, we basically split that up and do finite differences of the evolved components in the orthonormal basis, which is fine everywhere. So those are regular and fine everywhere. So you can finite difference through the origin and through the axis. And you take analytic derivatives of the scale factors. So you do basically a product rule and write it out that way. And that is later going to be expressed in the code. So as I said, if that was in Cartesian coordinates, then one of the terms obviously goes away, and the scale factors are 1 everywhere. So you would write that out by hand, but because it becomes much more complicated in the spherical case, you actually generate the code using Python.
Can I ask you? I don't understand the advantage of what you're doing. I mean, you actually wrote down you're not regularizing at the origin. So basically, it's better to use a Boyer-Lindquist, I would assume. And I would imagine that you run into trouble at phi equal to 0 at the top if you're trying to move things back and forth there.
Yes, so that's what I'm going to talk about in the next slide. So we never actually have a point at the origin or the axis. So we use a staggered grid.
So you're assuming that you simply don't have a flow there, basically? There's no material in the axis?
No. We don't make any assumptions. So we have a staggered grid. So the cell centers are the theta half of the axis, right? And then you have cell faces that are actually on the axis. And because we evolve everything in the orthonormal basis, the code or the evolution system only knows about the geometry by cell-centered source terms that are geometric there. So we don't make any assumptions about that. But if, sorry?
I don't see how it works really, because you run out, it will give you trouble because the physical size of the phi equal to 0 would be very small. So if you try to shift things there, it will limit your computation by considerably. It will slow. Basically, it will slow your computation.
Yes, that's what I'm going to talk about later as well. So,
Okay. On the origin, why not wire linkwist or something like that?
well, we want to it's an evolved spacetime, so we don't do fixed backgrounds. So,
Oh, okay.
right, you have a hypermassive neutron star. You cannot treat the spacetime as fixed.
Okay. That's okay. All right.
All right. So the way we do this is if you take a globe that sits on your desk and you cut out the z-axis and then cut open the globe at one meridian in phi, you can actually unroll the sphere into a topological Cartesian coordinates in a one-to-one fashion. So the fact that you need multiple charts to cover the sphere is only due to the fact that the axis basically is ill-defined. So our coordinates run from dr half, so that's where the first cell center is in the radial direction, to dr max, and then in theta you go from d theta half to pi minus d theta half, and that can be as close as your actual resolution in theta is. So, and most importantly, the cell faces between the first point in phi and the ghost zone in phi is at the axis. But we don't, all our evolution is cell-centered, so we don't evolve any fields on the actual axis. And then phi is a regular coordinate, so there's no problem. So you just use a periodic coordinate in phi. And what you need is you need internal parity boundary conditions in order to do finite differences and reconstruction in finite volume schemes. So you follow rays through the origin and basically take the values of the ghost zones on the other side of the radial ray by using the live points in the spherical grid on the other side of the origin. And you have to multiply them with appropriate parity factors. And you do the same as you go across the North and the South Pole. So those are completely internal boundary conditions. So in our case, we have only one coordinate that has an actual outer boundary, which is the radial one, where we have to supply outer boundary conditions at the R plus boundary or R max. Whereas all the other ones, so the internal R min boundary, the theta boundaries, and the phi boundaries are given by those internal parity boundary conditions. And how that works is, again, if you want to do that, it's easiest to unroll the sphere into a Cartesian cube and then see how you have to manipulate the R and theta. So at the R0 boundary, you go from R to minus R. Theta, if you follow the origin, goes from the theta point that was at theta to pi minus theta, so on the other side. And phi is switched around by pi. And what I did is I developed this algorithm to basically take subarrays in 3D slabs and manipulate them, broadcast them into the ghost zones, and then multiply them by the appropriate parity factors. And if you do that, your boundary conditions are internal. So there's no, the actual value of the field on the other side is given by the evolution of the field on the other side. So that is, I guess, partly answering your question. So you actually evolve the metric and you take the other side of the rays through the origin and along the meridians to actually do the finite differencing. And the same for Hydra. If you have the density on one side of the origin, then you fill the ghost zones by the other side and then use that to reconstruct the density and all the other Hydra quantities in your finite volume algorithm. And
does that create all sorts of non-localities that interfere with parallelization?
Yes. So the algorithm is fully MPI parallelized. So if you can have an arbitrary domain decomposition, and then the algorithm is actually able to, regardless of the domain decomposition, fill in the ghost zones. And it's written in such a way that you can schedule, if you wanted to solve a different physical system in the spherical coordinates, you could just use my boundary routines and schedule your functions, and they would be called. So yes, we had that in mind. Because normally it is, I mean, the communication is non-local, right? There's no reason to assume that the data you need in order to fill the ghost zones on the other side of the origin might live on the same processing. Okay, now let's go back to the double FFT filter. So what we do is we evolve the equations with a time step that is way too large for the actual grid, which means that in an unfiltered run, because the time step is too large, you basically start growing all the CFL unstable modes in the grid exponentially, which quickly leads to catastrophic failure of your code. But we actually perform an adaptive FFT filtering by damping those CFL unstable modes at a given radius and latitude. So filtering in phi is trivial in a sense, because phi is periodic. And in order to filter theta, we actually do the same thing. Well, conceptually similar thing to what we did with the boundary conditions is basically we take the data from 0 to pi, so 1 gray in theta, and then we extend it on the other side to basically make theta periodic as well. So you fill in a larger, which is now 2 from 0 to 2 pi, theta array by using the data from 0 to pi, and then the data from pi to, again, 0 to pi, multiplied by the corresponding parity factors, and then you filter in that larger theta or double theta coordinate. And you filter, the theta filter only depends on the radius. So you filter all the modes that are unstable at a given radius, and then there's a cutout where you don't need to filter anymore because the time step in the theta direction is given by RD theta. So when your RD theta is larger than dr, then you can stop filtering because you want to be limited by the radial direction. And once you've done that, you filter in phi as well, and the phi filter is now a function of radius and latitude. So you basically want to have equiangular resolution when filtering in the theta and the phi direction. And that's what we implemented, and that works really well for the space-time. And we still need to work out some things connected to GMHD. So GMHD is already tough without the filtering, and with the filtering, we're seeing that at least some of the problems we're still having problems with the filter. But I'm going to show some results with the double filter later. And then finally, I talked about that it's difficult to write down these equations by hand. So here's a snippet of what the code actually looks like in Python. So we're doing that with NRP+, which was developed by collaborators. So here I want to calculate the theta right-hand side. Theta is the variable in the constraint damping that basically is responsible for damping the Hamiltonian constraint. And you see that you write down the code almost as if you were writing it down on paper. So you do for loops and all that, and you calculate your final right-hand side. And what the code is actually outputting is doing a common variable name elimination, and it basically outputs hundreds of lines of C code with lots of temporary variables, and the final code that comes out is that horrible looking expression. So you'd never want to write that out in C by yourself. And the other nice thing about this is that it's easy to do different coordinate rescalings and all that, because under the hood you can already do that. So when we finally got non-constant radial coordinates, we just needed to rerun the code for that new radial coordinate and basically construct new include files for the evolution code. All right, and then let's have some nice results. So that's one of the results of the early code with pure vacuum. So I'm going to show an evolution of a Bowen-York black hole, which is a conformally flat initial data for a spacetime that mimics a rotating Kerr black hole. The fact that it's conformally flat is a problem, because we know that the Kerr spacetime is not conformally flat. So this is basically a Kerr black hole plus some junk radiation that is going to propagate out and disturb the black hole, and the black hole will start ringing. So here I'm plotting psi4 as a function of time. So the initial radiation is leaving the system, and then there's some partial reflection at the outer boundary, but you basically see that those concentric rings that go out of radiation basically travel out undisturbed. And if you were to contrast that with Cartesian coordinates, and if we have time later and people want to actually see it, I have some plots comparing the fidelity of the gravitational waveforms of the ring down, comparing them with Cartesian coordinates. But I mean, nobody really wants or needs a new vacuum code to just do single black holes. So we needed to do a GMHD at some point. It was working really well for that problem in vacuum, but as I said, I mean, we wanted to go further and actually do matter as well. So we compare the black hole mass and spin evolution between our spherical code and a Cartesian reference code that was already in the Einstein toolkit. And we see that if we choose a high enough angular resolution in order to capture the physics of the rotating black hole, then we perform much better in terms of both the irreducible mass and the spin evolution of the black hole. And the problem there with the Cartesian code is basically that those reflections where the initial gravitational wave is traveling out and then it gets partially reflected, so it comes back and it disturbs the black hole again. And that causes secondary ringing in the black hole, and those are all those wiggles that you see here. Whereas in the spherical case, you just unobstructedly go out until you then will be affected by the incoming stuff from the outer boundary. But that was a very important test to show that the code was actually doing what it's supposed to be doing in vacuum. So let's go to matter. What I'm going to show here is a magnetized, differentially rotating neutron star that is susceptible to the bar mode instability. So I cut off the first 2,400 M of evolution because it takes a while for the instability to grow. So you perturb the star by perturbing the pressure inside the star with random perturbations. And then it forms a bar mode where from originally being spherical, it basically forms like a bell shape of a M2 mode in the star. So here's the evolution for that. So that's with the dynamical spacetime, which is why we have to do all what we have to do. And you basically see that you formed that M equals 2 mode, and then the M equals 2 mode decreases in strength, and then you form an M equals 3 mode where that is dominant, and then the end becomes M equals 1, and then it settles down to a quasi equilibrium configuration towards the end. And you form a star with a very light disk around it. And that was magnetized with the filtering in both theta and phi in order to get a much larger time step than would have been given if we would have done that without any filtering. And to show that the code, again, is doing what it's supposed to do, I'm plotting here the amplitude evolutions of the M equals 2 azimuthal mode of the density evolution. So what you basically do in order to quantify the mode growth is you do integrals of e to the minus im phi of the density, and then you pick out the M equals 2 mode because that's the bar shape. And I'm also plotting on the same plot, I'm plotting the L2 M2 mode of the gravitational wave strain of psi4. And I basically shifted them by multiplying. I don't remember which one I multiplied. I think I multiplied the psi4 by a constant in order to put them on at the same height. But it's a constant everywhere. And then the detector was at 1,600 M, so you had to subtract the time it takes the signal to actually reach the detector in order to align them by time. And you see that there's a really nice correlation between the growth of the M equals 2 mode in the star and the actual emittance of gravitational waves. So it's another nice result to show that the code is doing what it's supposed to be doing. And then finally, I started playing around with that, and then I didn't really have time to continue. So that's something I want to go back to at some point. So the code was written with the post-merger phase in mind, but if you choose high enough angular resolution, you might think that, well, maybe spherical coordinates are not really the optimal coordinate system in order to do binary systems, right? Because I mean, it would be easier to follow the stars with either co-rotating or fixed Cartesian meshes that follow them around. But if the angular resolution is high enough and you can do everything in the same grid, then you wouldn't have to pass data from a Cartesian simulation to a spherical simulation with all the associated noise that comes from the interpolation process. So if we have high enough angular resolution, and we can actually do that because we have to filter, so the time step problem is not that high, we might think about being able to actually do a full merger simulation in spherical coordinates, and then the resulting system, which is a hypermassive neutron star, or in this case, because it's a really massive binary system, is a direct collapse to a black hole. The resulting system will directly be in the coordinates that are adapted to the symmetry of the system. So I tried that just to see if it was working. And here's how that looked like. So you have a merger of two very heavy neutron stars, and then you see prompt collapse to a black hole, and then some spiral density waves in the resulting disk, and then some dynamics. And so that's showing that the code can do a simulation of a very dynamic system and dynamical collapse to a black hole in an actual merger simulation. So that took quite some sleepless nights to get that working. And finally, as last result, just the collapse of an equilibrium model, which is a rapidly rotating neutron star. And again, we perturb it. We deplete a bit of pressure, so we remove like 5% of the pressure initially in order to trigger collapse. And here I'm showing different measures of masses. So we have the total rest mass, and we have the coma mass and the ADM mass, and finally the black hole mass. And we see that all those masses basically agree. So the star is perturbed in such a way that the collapse proceeds, and all the material is basically swallowed by the resulting black hole, and that's what we're showing here. So you see at the time of the collapse, the rest mass drops drastically when it's being swallowed, and then the black hole mass and the ADM mass agree very well. All right, and then I have, I think, 2 slides to show some next steps. So the first improvement is algorithmically and computational. So we need to have better parallel efficiency. And the main problem with that is that the FFT filter is currently not MPI parallelized. So if you want to filter in the phi or theta direction, you cannot domain decompose in the phi or theta direction. That is alleviated at the moment by the fact that we're using hybrid MPI OpenMP. So you basically use less processes but more OpenMP in order to still be able to use more cores, but that's only going to get you so far. So what you really want to do is have a parallel FFT. So possible strategies would be to have parallel and batched FFTs, or what you could also do, you could fill the rings that you want to filter by communicating the data, then filtering locally, and then communicating the filtered data back. So we have to see what we're going to do there, and who's going to have the time and money to actually do that. Regarding GPUs, there are current efforts in the Einstein toolkit to enable hardware acceleration by using AMRX for fully adaptive mesh refinement instead of the old carpet driver, which is the current box-in-box mesh refinement driver. And the idea there, again, our building principle has been to use as much as possible of the Einstein toolkit in order to not reinvent the wheel. So once AMRX is ready, we could see that we can build on top of that, and then we would have to do our own offloading. So my current plan for that in the future would be to use OpenMP offloading for the right-hand side in order to perform those calculations on the GPU, and then be able to harness heterogeneous hardware. But one of the questions is that as the code becomes more efficient, the question is, are we kind of optimizing us out of exascale? So here at Oak Ridge National Lab, for obvious reasons, exascale is a big thing because we're going to have the first exascale machine this summer being installed. And the way computation here at the lab works is that one of the figures of merit you have for your simulations is if you can run at scale. So if they have an exascale machine, you have to actually show that you're running simulations that need exascale. And what we've done with spherical coordinates is basically, if you remember the earlier plot where I showed you the Cartesian setup with the box-in-box mesh refinement, we went from something that was Cartesian to spherical coordinates because we realized that using Cartesian coordinates in full 3D with large domains is completely inefficient. So we invented, or we spent a lot of time writing a code that is as efficient as possible, but that also means that we're not going to really use exascale resources, right? None of the simulations I've presented here will actually need exascale because there's just not enough points. And I think that's a problem in general with algorithms that become more adaptive and more, yes, they have more adaptive grids and use the resources as clever as possible, is that, I mean, we just don't have enough work to do. Neutrinos or other different more physics might come to the rescue. So if you do full neutrino transport, you can use, if you use 80 energy bins, then you have to evolve 80 times 6 species of neutrinos at every point. So now you multiply the total workload you have by a lot. So you can use neutrinos to get where you want, but that is, you have to see if that is also going to be enough. And maybe another opportunity would be to do ensemble runs, where you basically say, well, a single run of mine is not going to be using 20% of an exascale machine. But if you give me an allocation on the exascale machine, I can run 10,000 binary Newton star mergers, and then we can actually start doing statistics, as opposed to just having a couple of hundred of simulations. So those are things that, since I came into the lab and was introduced into that new world of bigger is better and all that, and going away from like small CPU clusters where you can do cool stuff, that is something that you have to think about going forward. And then finally, we also need more physics. So currently we only have numerical relativity and GMHD. So we're missing a realistic EOS framework on neutrinos. So for nuclear EOSs and neutrino opacities, a possible strategy would be to interface that with weaklib, which is what I'm actually paid to work on here at the lab currently. So I'm not really paid to continue my work on SphericalNR. I do that in my free time at the moment. Use weaklib for EOS and neutrino opacities, and then use those to interpolate in the Einstein toolkit. And we could do leakage as an intermediate step, where you basically, as I said, you remove energy and momentum via the neutrinos, but there's no back reaction. Or maybe it's better to just jump directly to do full neutrino transport. So here at the lab in my group, there's a code being developed that using a two-moment model for neutrino transport using discontinuous Galerkin methods, which is also GPU aware. So we could think about interfacing that tornado code in the Einstein toolkit as a more of a long-term plan to get neutrinos into the code. But we'll see where that goes and if there's funding and what we can do. But it's certainly something that is on my mind going forward that I would want to do. And yes, a final, is that the final one? No, okay, two more, sorry. So some of the computational challenges for numerical relativity in the exascale era is that we have really high spatial resolutions, which means the time steps are small, and then we need lots of time steps to actually get to the full extent of the simulation. So if you have of the order of 10 to the -8 seconds and you need a couple of 100 milliseconds, which is the current state of the art for long-term evolution of hypermassive neutron stars, then that's going to be millions of time steps. And the simulation is similar in core collapse supernova. So the main problem is that there's a large range of physical scales, and you need to resolve the smallest scales with a very high resolution for a very long time in order to get the large scales of the system. And as I said before, without full neutrino transport and efficient mesh refinement or spherical coordinates, those are not exascale simulations there. So it's the problem size is just it's just too small. So we have to think about what we're going to do there. And finally, if that's like law and folklore in the numerical relativity community, is that numerical relativity simulations tend to not scale particularly well. And that is because solving the BSSN or CCZ4 equations, you have to evolve 24, 25 fields with either of the ones. You need higher order finite differencing plus higher order time integration. So you need RK3 because solving the scalar wave equation is unstable with RK2 even in Cartesian coordinates, and the BSSN equations are basically glorified wave equations for the metric components. So RK3 means you need to do more steps, which increases the computational cost. The time step is a bit larger with RK3 than RK2, but not enough to offset that extra step where you have to do a full right-hand side calculation and synchronization and all that. So a full extra mini time step. And you need higher order finite differencing, which means you need lots of data that needs to be communicated. So the MPI syncing between processes is very large, and that takes up a lot of time. And if you want to use higher order reconstruction methods in GMHD, that also requires a large number of ghost zones. So I've been doing some runs with MP9, and that requires 5 ghost zones. So you might end up in a situation where you're almost communicating as much data as you're actually solving on your grid, and that is not really efficient either. And one possibility is hybrid MPI with OpenMP, but in my experience, that hasn't really been shown to scale as well, or at least not better as pure MPI. And a possible solution to this problem would be to use something like discontinuous Galerkin methods, which only require 1 ghost zone to be communicated between elements on adjacent processes. And that would obviously be a huge help with that problem, because you go from communicating 5 cube ghost zones to only 1 cube ghost zone. So that would help tremendously, and that's what the Spectre people are basically after. Well, they're also doing task-based parallelism, but that apart, I think that is something that people have to keep in mind. And then finally, GMHD is not particularly well load balanced. So in reconstruction, depending on what you do, you often require limiters. So for instance, PPM and MP 5 to 9, they all need you do a polynomial reconstruction. Then you need to limit the phase values in order to guarantee monotonicity and things like that. So if your solution is smooth, then basically you just construct the polynomial and you're done. If you're in the presence of a shock, then you have to do all the limiting. So you're basically in different parts of the grid, you're spending different times on that. Then you need to do some root finding to invert the conserved variables and get the primitives. And even most importantly, like in a typical binary Newton star merger simulation, a large fraction of your computational grid is actually like a tenuous atmosphere where the inversion is often skipped and the reconstruction is trivial because it's just isotropic. If you have a like mesh refinement and a non-radial coordinate, that helps, because while the total volume is might be a large fraction of the total volume might be the atmosphere, if the cell sizes are larger, it means that not necessarily you have more points of the atmosphere. But in many cases, you might still have a situation where, let's say, half of your total points are actually atmosphere doing the majority of the evolution, and then there you basically, I mean, you have to solve the field equations because you don't have boundary conditions there, and you have to solve the hydro, and the load imbalancing might be a problem there. And I think that's also a reason why the Spectre collaboration is trying to use task-based parallelism, where you basically give all your points to tasks and then just go through them, and that would help with that. So here's a list of my collaborators. Sorry, I ran significantly over, but yes, I hope I gave you an overview of what I've done, what the code is about, and also some depending on how you see it, scary outlooks into the future and what we can do there. So thanks everyone for their attention.
So the BNS simulation, does it launch a jet?
Not yet. That was just proof in principle to see whether we can get the dynamic collapse. So I didn't want to go into details, but the double FFT filter, we actually had to do quite a few tricks in the presence of a black hole. So there's some algebraic constraints in the equations, and when filtering and in the presence of a black hole, it turned out that we had to enforce some of those algebraic constraints in a different way than we would normally do, and we're not really quite sure yet. So that was really just proof of principle and going forward. But yes, that was one of the questions I want to answer in the future, or hope that the code is going to help other people answer those questions in the future, right? So
Any other questions? Going once, going twice. Okay, I'll stop the recording.